Hello, my name is Cameron Allen. I am a graduate student at the University of Nevada, Reno, and today I'd like to present developing X-ray Fresnel diffractive refractive radiography for measuring mutual diffusion in warm dense matter. This is an experimental platform being developed by an international collaboration of scientists for use on large laser facilities such as Omega and the National Ignition Facility. To begin, we're defining mutual diffusion as a diffusion process due strictly to density gradients within our system. Means it is separate from temperature-driven or pressure-driven diffusion, and we are solely concerned with an initial concentration gradient between two materials within the system. As the picture in the middle shows, while both materials start in very separated and clearly delineated regions, after some amount of time, they will start to mix, and we end up having a diffuse boundary. Mutual diffusion is characteristically slow, occurring over relatively small distances of perhaps a micron scale length on a rather slow time scale of upwards of 10 nanoseconds. So this is a very fine, small process, but requires a long-lasting sample. Mutual diffusivity is an interesting topic of study as it is thought to influence a wide variety of phenomena across the universe. Of particular interest is its applications in warm dense matter systems, where a better understanding of mutual diffusivity can help inform these other processes. This includes things like the atmospheric stabilization and heavy element abundances in white dwarfs or neutron stars, or things like the transport properties and planetary magnetic field generation of Jovian planets. But perhaps most importantly to our collaboration's research is the thought that Rayleigh-Taylor instabilities are influenced by mutual diffusivity, and this is going to find widespread applications in both astrophysical fields as well as inertial confinement fusion efforts. In order to begin to measure mutual diffusivity, we have first been working to develop a platform that will allow for a stable interface between two materials heated to warm dense matter conditions. A top-down overhead diagram is shown on the left. We use an embedded wire system consisting of a 10 micron diameter aluminum wire that has been coated with 200 micron diameter plastic. This embedded wire is then isochorically heated by an X-ray bath provided by silver L-shell X-rays and probed over time with a vanadium helium alpha X-ray. The time evolution of the system's density is shown on the plot on the right. For diffusion measurements, we would be interested in the region from about 1.5 nanoseconds onwards to limit the expansion-driven smoothing of the density gradient. But we are also interested in the early time changes of the system as well. We have termed the imaging setup for our experiments Fresnel diffractive refractive radiography, which is in itself a form of refraction-enhanced radiography developed by some of our collaborators. In order to measure the micron scale length changes in our system that we expect, we must first ensure that we can see them. In order to do this, FDR leverages both absorption and phase contrast imaging, common to X-ray imaging, wherein we have a micron-sized source to ensure the high spatial resolution to see micron-sized objects, and then adjust the geometry to allow for a larger phase contrast to better resolve the density resolution. Putting this all together, this allows us to see the thin wires, resolve any changes in their density, and this is all based on the diffraction-refraction patterns generated by the probe X-rays. Based on the size of our objects and the parameters for our experiments, we are dealing with Fresnel diffraction, hence the Fresnel diffractive refractive radiography. Given the cylindrical nature of our targets and the spatial resolution constraints that I mentioned earlier, we decided to use thin slits as our X-ray source. The thinner the slit, the better we will be able to see anything. This is based on the idea that source size and target density will influence our overall signal. The sharper density gradients will produce stronger diffraction features, but in order to see those sharper density gradients, we need to have a much smaller slit. We also know that the density gradient will smooth out over time as the two materials diffuse, which will result in less strong features. Therefore, if we start with a smaller slit, we are able to get sharper features and better be able to time resolve as the pattern changes and work out the density. The simulations on the right show an identical system with a number of different slits. The thin slit, the 1 by 30 micron slit, you can see very sharp diffraction features or refraction features within it. But as soon as we start making this slit larger, those features get washed out until the point where even at 5 micron wide slit, it's still very small, we won't be able to tell much even at the beginning, and it will just get worse as the density gradient smooths out. Therefore, we've produced and utilized 1 micron slits, such as the one imaged in the middle here, for use on all of these experimental platforms, which, to the best of our knowledge, are the smallest slits ever used at a large laser facility. Looking now at actual data, we begin with calibration shots, imaging numerous wires and serving as the initial conditions for comparison to the later driven targets. At left, you can see one of the strips from the camera above its lineout, and the various wires are clearly visible. We have tungsten on the left to serve as an absolute zero. You can see a very clear refraction signal from the boundary of the epoxy with vacuum. And then you can see 2 different aluminum wires, one of which, the one more towards the middle of the strip, is actually embedded inside this epoxy cylinder. That same aluminum in epoxy we can match to simulations, which are shown at the right, serving as a good indicator that we are able to see relatively what we're looking for. The calibrations as a shot as a whole also serve to demonstrate the ability to align the slit and get signal through it, which is always a success on the day. When we look at the driven target data, we see significant changes, though that is to be expected. The calibration targets, where they're cold, there's no drive, show a very strong, very sharp density gradient. And that's shown on the left side of the figure on right, where we have that previously shown refraction pattern overlaid on the data, and we can see the density profiles that make that up below it. However, the driven target is lacking any of the sharp refraction features, and its density profile to fit it, it looks markedly different. And in fact, we're seeing a scale length change in the interface of almost 5 microns. This is something we're still looking into, trying to understand, and working to resolve moving forward. Speaking of moving forward, we have 2 campaigns upcoming to further work on this idea. The first is an LBS campaign at Omega in late February 2021. For this, we will be working with the aluminum inside the plastic again. This is to better resolve that pattern change and work out kinks in the alignment and better understand everything before we move on to a campaign at NIF about a year later, wherein we'll be switching to lower Z elements. Liquid deuterium and CH is the current plan, and this is going to be to help increase the diffusion rates and is more applicable to ICF. The images at right show the ideas for the NIF campaign with a layout at the top and then the simulated diffraction pattern showing how the diffusion will affect the signal over time. In summary, mutual diffusivity is a transport property that's in need of experimental benchmarking for warm dense matter for astrophysical relevance as well as ICF importance. Towards that end, we're developing a diagnostic termed Fresnel diffractive refractive radiography for use at large laser facilities such as LLE and NIF to capture micron scale changes in the density to measure the diffusion coefficient. We do this by measuring diffraction patterns, which then inform us about the change in densities. And to develop this, we have conducted experiments at LLE, and we have upcoming campaigns again at Omega in February 2021, and as well as NIF and Q2 FY 2022. Thank you very much for your time, and we'll take any questions. Thank you.